In the previous video, we introduced some of the concepts about statistics that we are going to use in our discussion about machine learning algorithms later on. Today, we're going to talk a little bit more about a few more concepts. Let's start with the joint probability distribution. So here we are talking about not just one random variable. We're talking about two random variables now, both x and y. And this joint probability distribution is just the mapping from any realized values of the two random variables, x and y, to probability, right? And these two random variables, x and y, can be scalars if it's a one-dimensional random variable, right? But it can also be vectors, right? If it's if the sample space is not one-dimensional, if it's like a multi-dimensional, right? So in that case, both x and y are going to be vectors, right? So and in the literature or in textbooks, this kind of joint probability distribution are usually denoted like that. So PR x comma y, that's the joint probability of x and y, equals to some kind of mapping f x comma y, right? So this is called the joint distribution, right? So we have two random variables, x and y, and they are taking upon realized values, small x and small y, right? So here we are not exactly making the distinction about the random variable itself and the value it actually is taking upon, right? In some of the textbooks, those random variables are capitalized, and then the values they are actually taking upon are small case letters. But here we are not really making that kind of distinction. But in our mind, in our heads, we have to sort of realize that x and y's are. We have to sort of understand that small x and small y are the realized values of those random variables. And a few points about the joint probability distribution. So if we have just one random variable, right? If it's just fx, then the integral of fx over x is going to give us 1, right? That's one of the axioms of probability distributions, right? The integral over x is just going to be 1. If it's a discrete sample space, then the summation over x is going to be 1. But here, because we have like two random variables, x and y, right? So we have to do two summations, double summation over all the possible values of x and y. And this double summation should equal to 1. This is for the discrete sample space. If it's a continuous sample space, we have to do a double integral over both x and y. And this double integral is supposed to be 1, right? Because of the axioms, because the first axiom of the probability density or mass function, right? And then we have to remember that the probability distribution has to be larger than or equal to 0. It cannot be negative, right? That's the joint probability distribution. And then we have to sort of consider something that we call marginal distribution, the marginal distribution. And because we have two random variables, x and y, right? So if we just do a summation over y, say, right? If we just do a summation over y, right, without doing a summation over x, then the result of the summation over y is going to be a function of x. The same is true if you do an integral over y, if the sample space is continuous, right? If you do an integral of the joint distribution fxy over y, then the result of the integral is going to be a function of x, right? So here we are denoting the result of the integral over y as gx. And this gx is called a marginal probability distribution for x, right? We're simply integrating this function with two independent variables over one of those independent variables, y, and then the result of the integral or summation is a function of the other independent variable. In our case, we're integrating over y, so the result is going to be a function of x, right? And this process of doing this kind of integral to obtain the marginal over x, the marginal distribution over x, is called marginalization. It's called marginalization, right? We can also do a summation or integral over x, and then the result of the summation or integral is going to be a function of y, right? Here we are denoting it as hy, and hy is called the marginal distribution of y, right? So after this marginalization process, what we have obtained is the so-called marginal probability distribution of x or y. One of the concepts that's closely related to marginalization is something that's joint probability distribution is something that's called a contingency table. It's basically x as a row, y as columns, right? And then it looks like a table, right? And then if you sum over all the rows, you are gonna get a result that depends upon only the columns. If you sum over all the columns, then the result of the summation is going to be dependent upon only the rows. And this kind of contingency table and the operations that we can apply on those contingency tables are similar to our understanding of the joint probability distributions and the process of marginalization, right? And if we sort of so here we have the marginalization of x, right? We have the marginal probability of x, right? So if we sum over x over gx, if we sum gx over x, then the result is going to be 1. The reason is because sum over x for gx is equal to sum over x, sum over y, fxy. And sum over x and y, fxy equals to 1. So the sum over x of gx equals to 1. The same is true for the continuous case. If you integrate gx over x, the result is still going to be 1, right? And if you actually sum over all the possible values of y for the marginal distribution hy, then the result is still 1. The same is true for the integral case, for the continuous case, right? So the marginal distribution, if you integrate it over all the possible values, it's still going to give you a 1. So in some sense, marginal distribution is actually a distribution, right? It's actually a probability distribution. It is actually a probability distribution, and we have to actually keep in mind that this very important property, right? And the next very important concept is the conditional probability distribution, which is actually the probability of x occurs given that y occurs. So this is actually the difference between conditional probability and the joint probability is kind of subtle. For joint probability, it is both x and y occurs. It's the probability of both x and y occurs, right? But here you have some kind of dependence now. It is the probability of x occurs given that y has already occurred. So how the conditional probability is actually represented, right? So the probability of x conditional upon y with a vertical bar is defined as the joint probability of both x and y occurs divided by the marginal probability that y occurs. So here you don't see x, right? So this marginal probability of y is on the denominator. So out of all the possibilities that y occurs, you count the probability, or so it is defined in terms of this kind of ratio of both x and y occurs, and the the probability of y occurs. And let's look at some of the very interesting properties of this conditional probability distribution. Here I'm just considering the continuous case, so I'm doing integrals, right? But if the sample space is discrete, you can just convert all the integrals into summations, and then the result is actually identical. It's not going to change anything, right? So if we consider the conditional probability of x conditional on y, then it's going to be the joint probability fxy over the marginal probability of y, hy. So it's still going to be, the conditional probability is still going to be a function of both x and y, right? So on the right hand side you have both x and y. So it's a function of two independent variables, both x and y, right? If both x and y, these random variables, are one-dimensional, you can visualize it in your head as with the x as the horizontal axis and y as the vertical axis, right? And then the value of the function is actually the axis that's pointing out of the screen, right? So it's a three-dimensional function, or it's a two-dimensional function, but you can visualize it using three axes, right? And then if you do an integral over x on this conditional probability of x conditional on y, then what's going to happen? The denominator is hy. It doesn't depend upon x at all, right? But you are doing an integral over x, so this integral can be carried over to the numerator, right? So it becomes fxy dx over x. And our previous slide actually defines the marginal distribution for y, right? The marginal distribution for y is exactly fxy integrated over x, right? So the integral on the numerator actually becomes hy, and then the denominator is hy. So hy over hy is exactly equal to 1, right? So this conditional probability, which is a function of both x and y, and then if you integrate over x, it's going to give you a constant 1, no matter what the y value actually is. It's a two-dimensional function, right? But no matter what y actually, what's actually the value for y, the integral of this conditional probability over x is always going to be 1. But suppose we integrate not over x, but we integrate over y. So px conditional on y over dy. Then what's going to happen, right? And in this case, we cannot actually take the integral just to the numerator, right? Because the denominator also depends upon y. So this integral has to be carried over the entire function. But is it going to be equal to 1? The answer is no. In general case, it's not going to equal to 1 unless you have very special sort of forms of the two functions, right? So in general case, it's not going to integrate to 1, right? So pxy, which is px conditional on y, this is conditional probability. Even though it's a two-dimensional, it's a function with two independent variables, but these two axes, x and y, has quite different properties, right? If you integrate over x, it's going to give you 1, but integrating over y, in general case, it's not going to give you 1. And this is actually a property that we have to remember. We have to actually keep in our mind, because this property is related to our distinction between conditional probability and another function that's called a likelihood. So the likelihood has exactly the same value as the conditional probability, but the likelihood is a function of y instead of x. So you have to actually treat x as given, and you are looking at the conditional probability as a function of y. But if you actually assume that y is given, and the conditional probability is actually a function of x, then the integral over x actually gives you 1. So the conditional probability is indeed a probability of x, right? But it's not a probability of y. it's likelihood of y, but it's not a probability of y, right? Because in general case, the integral over y is not going to give you 1. And this is x conditional on y, right? But we can actually switch the role of x and y. We can use y conditional on x, right? And if that's the case, then the definition of y conditional on x is going to be fxy, the joint probability, divided by gx, the marginal of x. And then if we actually integrate over y, right, we're going to get exactly 1. Right? But if we integrate over x, in general case, it's not going to equal to 1. Right? So py conditional on x is a probability of y, but it's a likelihood of x. It's not a probability of x. Right? And later on, once we talk about the Bayesian, we will talk more about likelihood and conditional probabilities. Right? So, it's a subtle difference, but it's actually a very, very important concept, the likelihood. Right? And then if we actually pay attention to these two equations, right? And for this equation, if we multiply hy on both sides of the equation, then we get px conditional on y times hy equals to fxy, right? And then if we multiply gx on both sides of this equation, then we have py conditional on x times gx equals to fxy, right? So that's this equation here. So fxy is equal to both px conditional on y times hy, and it also equals to py conditional on x times gx, right? And because these two functions equal to the same function, the same sort of function, the joint probability distribution, then these two functions must be equal to each other, right? So that's the result here. So probability, the conditional probability of x conditional on y times the marginal of y must equal to the conditional of y, the conditional probability distribution of y conditional on x times gx. And then if we actually divide gx on both sides of the equation, then we have obtained another expression that's py conditional on x actually equals to px conditional y times hy divided by gx. And this is one of the forms for the Bayesian theorem. And each of the distributions in this particular equation actually has specific names. This is the marginal for x, right? But this function hy, the marginal for y, is called the prior distribution for y. And this px conditional on y, it's a conditional probability for x, and it's also the likelihood of y. And on the left hand side, py conditional on x is called the posterior distribution of y. And why do we have those different kind of names associated with those different probability distributions? We'll talk about that when we talk about the Bayesian theorem in the next video.